Imagine standing on a bridge, when the ground beneath you suddenly moves with the force of a massive earthquake. The road begins shifting, the towers move, the cables start vibrating. But instead of collapsing, the bridge is designed to move with the earthquake. Japan has some of the most earthquake-resistant infrastructure on Earth. And one of its greatest engineering achievements is a bridge system designed to survive forces powerful enough to completely destroy ordinary structures. But how do you build something that can move without breaking? Japan doesn't try to make bridges completely rigid. That would actually make them more vulnerable. Instead, engineers design the structure to absorb energy, distribute forces, and move in controlled ways. Every tower, cable, bearing, and connection has a specific job, and the most important part of the system is hidden inside the structure. To understand it, we first need to understand what an earthquake actually does to a bridge. When people imagine an earthquake-resistant bridge, they often picture an incredibly strong structure that simply refuses to move. But that's not how earthquake engineering works. An earthquake doesn't just push a bridge in one direction. The ground can suddenly move sideways, vertically, and back and forth in complex patterns. A massive bridge sitting on that ground has enormous inertia. The foundations move with the earth. But the bridge deck and towers resist that movement because of their mass. That creates powerful forces inside the structure. And here's the problem. Making the bridge completely rigid can actually make those forces worse. If the structure cannot move, earthquake energy has fewer places to go. Instead of allowing controlled movement, the force can concentrate in critical components. Engineers therefore use a different philosophy. They design the bridge to move safely. Flexible structural components can deform without immediately failing. Special bearings allow controlled movement between different parts of the bridge. Energy dissipation devices can absorb some of the motion before it reaches vulnerable components. The objective isn't to stop the earthquake. That's impossible. The objective is to prevent the earthquake's energy from turning into catastrophic structural damage. This becomes especially difficult for a long suspension bridge. A bridge spanning several kilometers cannot behave like a simple building. Its towers, cables, deck, and foundations all interact. If one part moves, that movement affects everything connected to it. So engineers have to predict how the entire structure will respond as a single system. And that requires understanding something most people never see. The bridge is designed to move before the earthquake even happens. The key to earthquake resistance is not simply stronger steel. It's controlled flexibility. A modern earthquake-resistant bridge can contain bearings, dampers, expansion joints, and flexible connections that allow different sections to move relative to each other. Think about what happens when the ground suddenly shifts sideways. If the bridge deck were locked rigidly to every support, that movement would be transferred directly into the structure. But controlled movement allows some of that energy to be absorbed. One important component is the seismic damper. A damper works somewhat like a shock absorber in a vehicle. When the bridge moves rapidly, the damper resists that movement and converts part of the mechanical energy into heat. That reduces the amount of force transferred through the structure. Bearings perform another important job. They support enormous loads while allowing the bridge to move in specific directions. This is critical because a long bridge naturally expands and contracts with temperature. During an earthquake, however, those movements can become much larger. The components therefore have to allow motion without losing their ability to support the bridge. Engineers also design the connections between the deck and towers carefully. These connections must remain strong during normal operation, but they also need enough flexibility to accommodate extreme movement. And underneath everything are the foundations. They transfer the forces from the towers into the ground. If the foundation fails, everything above it becomes irrelevant. So earthquake resistance isn't one device. It's a chain of systems working together. The deck moves. The bearings accommodate movement. The dampers absorb energy. The towers distribute forces. And the foundations transfer those forces into the earth. But Japan faces another problem. The earthquake doesn't always come from directly underneath the bridge. Sometimes the most dangerous movement begins far beneath the ocean. A suspension bridge is already a moving structure. Its enormous deck hangs from cables. Its towers rise hundreds of meters above the ground, and the entire system is constantly responding to wind, temperature, traffic, and its own weight. Now at an earthquake, the ground can suddenly move sideways while the bridge deck tries to continue moving in its original direction. That difference creates enormous forces. So Japanese engineers designed the bridge around a simple principle. Don't fight every movement. Control it. The deck is connected to the towers through systems that can accommodate carefully calculated movement. When seismic forces arrive, different components are allowed to respond at different rates. This prevents one sudden movement from concentrating all the energy in a single connection. But controlling movement requires accurate prediction. Engineers use computer models to simulate how the bridge responds to different earthquake scenarios. They can change the direction of ground motion, the intensity, the timing, and the frequency of the shaking. Then they observe how the deck, towers, cables, bearings, and foundations respond. This is important because earthquakes don't produce one simple push. They create complex vibrations. Some movements are slow, others are extremely rapid. A bridge that performs well under one type of motion may behave differently under another. That's why earthquake-resistant design uses multiple layers of protection. The main structure carries normal loads. Flexible components accommodate movement. Dampers absorb energy, and specialized connections prevent excessive displacement. The objective is not to make every component equally strong. Instead, engineers decide where the structure should move and where it must remain stable. That idea becomes especially important for one of Japan's greatest suspension bridges, because when engineers designed it, they knew the earthquake could be extraordinarily powerful. One of the most remarkable tests of Japanese bridge engineering came from an earthquake that engineers never wanted to experience. On January 17, 1995, the Great Hanshin earthquake struck near Kobe. The earthquake reached magnitude 6.9 on the moment magnitude scale and caused catastrophic damage across the region. And something extraordinary happened to one of Japan's most famous bridge projects. The Akashi Kaikyo Bridge was still under construction. Its main towers had already been erected, but the bridge was not yet complete. The earthquake moved the ground beneath the construction site, and the movement was large enough to change the geometry of the project. The distance between the main towers increased by roughly a meter. Think about what that means. A bridge designed with millimeter-level precision suddenly had its foundations move relative to each other. Engineers had to inspect the structure and reassess the entire design. The bridge had survived the earthquake because its foundations and structural system were able to accommodate the movement. But the event also demonstrated something extremely important. Earthquake engineering cannot simply depend on theoretical calculations. Real earthquakes can reveal conditions that models never perfectly predict. The bridge design, therefore, had to be adjusted to account for the changed geometry. The final structure was completed with modifications to accommodate the new conditions. And this became one of the clearest demonstrations of Japanese earthquake engineering in practice. The bridge didn't need to remain perfectly still. It needed to remain structurally safe while the ground moved beneath it. That distinction is fundamental, because the goal of earthquake-resistant engineering isn't to create a structure that never moves. It's to create one that can move, absorb energy, and still carry its load when the shaking stops. But the towers were only part of the challenge. A suspension bridge carries its enormous deck through a carefully balanced system of forces. The main cables stretch between massive anchorages and pass over the towers. From these cables, thousands of vertical hangers connect down to the roadway. Together, they distribute the bridge's enormous weight across the structure. But during an earthquake, those cables face a completely different challenge. The towers can move, the deck can shift, and the distance between different parts of the bridge can change within seconds. The cables must absorb these changing forces without losing their ability to carry the roadway. The Akashi Kaikyo Bridge uses thousands of high-strength steel wires bundled together to form its massive main cables. This approach provides redundancy. Instead of depending on one enormous piece of steel, the load is distributed across thousands of individual wires. But strength isn't enough. The bridge sits in a marine environment where salt and moisture can cause corrosion. So protecting the cables becomes just as important as making them strong. Engineers use protective systems to keep water and contaminants away from the steel wires and maintain the cable's long-term strength. The bridge deck also needs flexibility. It must respond to wind, temperature changes, traffic, and earthquakes without allowing dangerous movement to build up. That balance is critical. Too much rigidity can increase earthquake forces. Too much flexibility can create excessive movement. So engineers carefully control how the deck and cables interact. And there is another force constantly attacking the bridge: wind. A structure this large can behave like a giant aerodynamic surface. If wind interacts with the deck at the wrong frequency, dangerous oscillations can develop. So before the bridge could be considered safe, engineers had to prove it could survive not only earthquakes, but also powerful winds. And that's where the bridge's aerodynamic design becomes critical. A bridge this large cannot simply be made stronger and stronger. At some point, adding more steel only makes the structure heavier, and more weight creates even larger forces during an earthquake. So Japanese engineers focused on something more important: controlling how the bridge moves. The Akashi Kaikyo Bridge uses a combination of structural flexibility, carefully designed connections, bearings, and damping systems to manage extreme movement. During normal conditions, these systems allow the bridge to respond naturally to wind, temperature, and traffic. During an earthquake, they help prevent sudden movements from concentrating in one vulnerable location. The towers carry enormous vertical loads, while the main cables transfer the weight of the roadway toward the anchorages. The foundations then transfer those forces into the ground. Every component has a different job, and that separation of roles is what makes the system resilient. Engineers also use monitoring and inspection to keep track of the bridge throughout its service life. Because earthquake resistance isn't something you design once and forget. A bridge exposed to wind, salt water, temperature changes, and traffic must continuously be maintained. The real engineering achievement is therefore not simply surviving one earthquake. It's creating a structure capable of dealing with thousands of smaller forces, while remaining prepared for the rare event that could be catastrophic. And that's why the bridge's greatest strength isn't its massive size. It's the way thousands of individual components work together. The structure doesn't try to defeat nature by refusing to move. Instead, it moves in a controlled way. And when the shaking finally stops, the bridge is still standing. A magnitude 9 earthquake represents an enormous release of energy. No engineer can stop it. No bridge can simply ignore it. So Japan chose a different strategy. Design for movement. Let the deck flex. Let the bearings move. Let the dampers absorb energy. Let the cables distribute the load. And let the foundations transfer the remaining forces safely into the ground. The Akashi Kaikyo Bridge is more than a road across the sea. It is a carefully balanced system designed around forces that humans cannot control. Wind, temperature, traffic, earthquakes. Every one of them is constantly trying to move the structure. And the bridge survives by controlling that movement. That may be the most important lesson in earthquake engineering. The strongest structure isn't always the one that refuses to bend. Sometimes, the strongest structure is the one that knows exactly how to move.